Hi and welcome. I'm trying to learn electrical engineering today with simple cell, and after we've done it, we're gonna do leg injury prevention training. And if you participate in the leg injury prevention training, then is at your own risk. Now, and this is part 2 of a simple cell. So, set up a simple cell by immersing a copper plate and a zinc plate in dilute sulfuric acid, and then connecting them to a milliammeter. Simple observation will give you the following information. Now, this is the setup.
There are copper and zinc plates in, connected with cathode and anode, and we have a millimeter, whatever.
I don't really understand it. Okay, and observation number 1 is the zinc plate gives off bubbles of gas, whether or not the cell is deriving a current through a millimeter, but more so when it is not. Second observation, when the cell is supplying a current, and only then, the copper plate is also converted with gas bubbles. The zinc is giving bubbles off all the time, but it's because gas exchanges happening or something. Because it's just dissolving. The zinc is dissolving in the sulfuric acid, I think. And the other one is giving, but it gives off less if the electric current is flowing. The other one, the copper plate, gives not off, but if current is flowing, then it gives off bubbles. And number 3, the current supplied by the cell becomes rapidly smaller from the instant it is first connected to the meter. I don't understand. Okay. Explanation of 2 goes on. Copper, unlike zinc, does not dissolve in dilute sulfuric acid, and the appearance of bubbles, hydrogen effect, on the surface of a copper plate is certainly not local action, but evidence of a general action of a cell. Zinc is dissolving in sulfuric acid, copper not. So the situation is like this. 3 types of iron are present in the electrolyte, from the water and acid. Okay, we're having water and acid. We're having H, hydrogen, O, oxygen, and some type of acid. We have H3O plus OH minus and SO4. What takes place when the ions wander towards the respective electrolytes? At the cathode, the hydroxynium ions lose their charge by gaining an electron. Some type of ions are wandering over to one of the plates and giving off their excessive, losing their charge, losing an electron, and have transported that way with the current. The copper does not dissolve in the acid. At the anode, atoms of zinc lose electrons and become ions which enter the solution. Okay, to one of the 2 things where we bring the current in and out again are going the zinc electrons, and they become then ions, and they are now part of the solution. This happens in preference to any sulfate ions being discharged. Whatever, I don't understand. So the zinc plate dissolves without any hydrogen being produced, in contrast to the local action mentioned earlier. Do they mean if there's no current, the zinc plate is bubbling even if no current is flowing? Do they mean if it is bubbling without that hydrogen is produced, then it is because there's no current flowing? The net result of these ion movements then is that the zinc plate dissolves, the copper is unchanged but covered with hydrogen bubbles, and the electrolyte progressively changes from dilute sulfuric acid to a solution of zinc sulfate, because the zinc is dissolving away, but it's not going completely away. It becomes part of whatever the thing there, of a solution, and it becomes now a zinc sulfate, a solution. I still don't really understand. To the observation number 3, I think is that now. The observation number 3 is the current supplied by the cell becomes rapidly smaller from the instant it is first connected to the meter. Okay, we're supplying current into it, and the current which reaches it or comes into it or whatever becomes smaller. Why does the current fall off as the cell is used? That is the question. A simple explanation is that the layer of hydrogen bubbles gets in the way and restricts the current flowing through the cell. Okay, the copper plate gets bubbles onto it as soon as the current is activated. And these hydrogen bubbles could be in the way for the ions to move and transport the current. Well, certainly the presence of a gas does increase the internal resistance of a cell. Yes, that is right what we have helped us to find out. That the bubbles are an obstacle in the way for the moving of the current, but it is not the complete explanation, which is rather too complicated to give here. This problem of the effect of a gas layer on the pole of a cell is called the effect of polarization. Why is it called polarization? Okay, it is for now too complicated why the current falls off, the amount of whatever it's now, the current falls off. But one part is because of the bubbles, a little amount of it, and that is called the effect of polarization. Now the gist, I don't know what gist means, of this involved explanation is that a simple cell consists of two dissimilar poles in an electrolyte. When you're talking about a cell, I think still that we're talking about a battery, but I don't know it. Okay, we are in a simple cell, maybe it's a battery we're talking about, are two dissimilar, I think that is the opposite of similar, so different poles in an electrolyte. We have copper and zinc. And the electrolyte is our sulfuric acid or whatever. This cell has two defects, and we're saying that it's something bad, I think. That would make sense. Local action and polarization, which must be overcome if a practical form of cell is to be made. Okay, it is a problem that there are the hydrogen bubbles, and also the local action is a problem. Local action, what was problem here? The one. And the zinc plate gives off bubbles of gas, whether or not the cell is driving a current through a millimeter, but more so when it is not. Zinc, unless 100% pure, dissolves in dilute sulfuric acid to form zinc sulfate and hydrogen gas. Zinc is just dissolving in our sulfuric acid, so we should maybe not use it. This process occurs in the cell when it is not producing electrical energy in an external circuit. It is a local chemical reaction involving only the zinc and the acid and is called local action. If your simple cell were left assembled for a few hours, the zinc plate would completely dissolve in the acid. This is, to say at least of it, inconvenient. Local action is said to be one defect of some cell. Okay, I understand. I think they mean that our battery by itself discharges. And if we build one out of zinc and sulfuric acid, that thing is in a couple of hours completely dissolved. So we're saying we have two problems. The first problem is these bubbles there. We have to get rid of these bubbles. And the second problem is the zinc plate dissolves. We should use something else than zinc. Before dealing with this next topic, we must note very carefully the meaning of some words we used earlier. And now in the next chapter is when the terms anode and cathode are used with reference to the passage of an electric current through an electrolyte. The current enters the electrolyte via the anode and leaves by the cathode. I don't know what it means. It's A to C. It's like alphabetically. Anode to cathode. This applies to both a cell supply. Okay, that means in the next chapter we're saying we're going to go through a few words to repeat it. That was electrical engineering. If you were here for electrical engineering, you can go directly to an expert for electrical engineering. We will do now the leg injury prevention training. If you stay and participate in the leg injury prevention training, then it's wieder on the square and you will stay in leg. The other leg will flex on in the air and we swing it around and back. From the other side. And with the other leg, swing it around to the side. And next exercise, one foot in front and back, front and back. And the other leg, stand good and bring it in front and back. Next exercise, pine pilcrow. Return this one leg up. We forward leg to the side. Again in into the middle. Up and down. Again in the other leg up. Out to the outside. Again into the middle. Down and down. Next exercise, one leg up and press with the knee up to the side. To the side. You can do it with a bit more force. And with the other leg, press with knee up to the side. And next exercise, the wildcatter. Stand good on one leg. This exercise can go to the knee. Stand good on one leg. Turn over to the leg. Go down. Turn over to the other side. And come up again. Other leg, stand good. Go over to the leg. down into the knee, then over to the outside, and come up again. And another time. Stand good on the first leg, turn over to the leg, go down to the outside, up, and with the other leg. Stand good, go to the outside, down, to the other outside, and before the direction warrior, one leg up, arms out, and turn with the hands over to one side. And to the other side. And one leg to the side, with a leg to the side, hands to the other side. And change. Middle and down, and the other leg up. Go with the hands over to one side. And to the other side. And hands over to one side and leg over to one side. And both. And the next exercise. One hand on tummy, one on lower back, and lift one leg in a straight line up. If the quad muscles cramp, and bring the leg up and point the foot up. Try to bring the leg higher. Flex foot, try to bring the leg higher. Control with the hands that you don't fall back. Try to bring the leg higher. And pull the leg up, point of the toes down, and relax the leg. And the other leg. Hand on tummy, other one on the back leg, back, and lift the leg up. Flex foot, try to bring it higher. Try to bring it high. And pull the leg up, point the foot down, relax the leg. And the next exercise, the clock can go again onto the knee. Stand good on one leg, and I'll go always in 90-minute intervals to the outside. And with the other leg. 12 o'clock, and 1:30, and 3, 10:30, and 9, and 7:30, 6, and also 4:30, and again the 3. And the next exercise, the pipette. Don't do it if you're pregnant. One leg points with the toes to the outside, other heel onto the ground, and lift the heel off the ground, and place it again on the ground. And on the other side, heel onto the ground, lift the heel off the ground, and place it again on the ground. And the step, and leg up and down, up and down. Other leg. And for horse, leg in and out. Other leg in and out. And the trunk igniter, legs wide apart, breathing that out. And breathe out again. And out. Breathing close the legs. And breathe again out. That was the leg injury prevention training. I thank you very much, and until next time.